So we're going to take a look at some direct and iterative methods for solving systems of equations. We're going to focus primarily on square systems, n by n systems that have a solution, but most of our methods can be modified to work in other situations when the system has multiple solutions. So some direct methods that we've seen before for solving a system. The inverse method, calculating the inverse of the matrix A. So we have the coefficient matrix, and so we calculate its inverse. And so in that case, then X would be A inverse times B. We've discussed on previous lectures about how many calculations are needed to find A inverse, and then how many calculations are necessary to do the matrix times the vector multiplication. So that's a two-step process: calculate A inverse and then multiply A inverse by the vector B. If we were solving the same system multiple times but just changing the right-hand side, then possibly we might consider the pre-computing A inverse and having it accessible. There are other issues with space and so on that we might be careful about and not necessarily choose that method, especially if the system is a very large system. Another approach would be Gaussian elimination. We have the augmented matrix where we have the coefficient matrix augmented with the right-hand side, the B vector. Convert that to an upper triangular form and then solve by back substitution. This method is called Gaussian elimination, named after the German mathematician Gauss, but versions of this method were in use as far back as the 10th century BCE. So elimination is a very old method for solving systems of equations. Again, we had a discussion about how many steps are necessary in Gaussian elimination to start with the augmented matrix and get to the point of having the actual solution. Another method is the LU decomposition. Again, we start with the same problem. We're going to solve a square system, A times X equals B. What we want to do is find a lower triangular matrix L and an upper triangular matrix U such that A is equal to L times U. Now, typically the approach to this is through Gaussian elimination. We do the Gaussian elimination steps to create the matrix in echelon form and keep track of the steps that got us there, and we can then construct both the matrix L and the matrix U. So what we do then is we think of U times X as being a new vector Y. We don't know X. We have calculated U. We know it, but we don't know X. So we don't actually know Y at this point. But we're thinking of U times X as representing this vector Y. And so since this is associative, we can move the brackets from LU to the U times X. And so we have then A times X equals B becomes L times Y equals B. We know L, we know B, and so we can solve for Y. L is lower triangular, and so we can solve for Y using forward substitution. Once we know Y, then we can return to the matrix vector equation U times X equals Y. We know U, now we know Y, and we can use back substitution to solve for X. And the X then that we get at that point is the solution to the system A times X equals B. LU decomposition is particularly useful if the right-hand side is going to change at different times, but the coefficient matrix remains fixed. Because what you can do is you can calculate L and U and have those pre-calculated, and then anytime the new right-hand side comes in, then we do the forward substitution and the back substitution steps to calculate the necessary values and solve for x to solve the new system. So this is not so beneficial if we are going to calculate a solution one time, because we've done a lot more work in this. We've created L, and we've created U, and we're doing forward substitution and back substitution, whereas with Gaussian elimination, we would only do the reduction and back substitute to solve the system. But if we have multiple right-hand sides, then solving new systems becomes just this matter of forward substitution, back substitution, and there's our solution. But sometimes a decomposition is not possible. The structure of the matrix A may not allow for the necessary kind of decomposition. But if we have a square matrix, then we can at least do a permutation of rows, columns, or both, and be guaranteed that we can create a new version of A that can be decomposed in this LU fashion. If a permutation of the rows is needed, we can create a matrix P that does a row permutation, and then the decomposition becomes P times A is the LU. If we need to permute columns, then it would be A times Q is in the LU, can be decomposed to L times U. If we need to do both, then we have P times A times Q can be decomposed in that LU format. Each of these, then, we need to think about how you would take that to solve the original system. But what happens is basically the permutations don't change solutions to the original system. Right? Permuting the rows or columns or both won't change the solutions, but it will change the order of the values in our answer. So knowing which value corresponds to which, there's a permutation of those values as well. So the LU decomposition is appropriate if we are going to solve several systems that all have the same coefficient matrix but different right-hand sides in this system of equations. So if the matrix A is unchanged but the vector B is going to change multiple times, then LU decomposition may be an appropriate choice. Other times, though, we want to apply other methods and other types of approaches that are typically faster or maybe easier to implement are some iterative methods. Iterative methods mean that we start with a guess at a solution and work our way to a solution, or at least hopefully work our way to a solution. So again, same problem. We're trying to solve the system A times X equals B. We know A and we know B, and we're trying to find X. So an iterative method would begin with an initial estimate, and we're going to often, in some cases, we would put a subscript to represent an initial value or initial guess. But in the case of a vector, we'll use this kind of superscript in braces to represent not the 0th entry in, or the entry at index 0, let's say, in the vector, but we're talking about a vector that is a starting point. And so we have an initial estimate of the solution. Often we just choose the zero vector or choose a vector that is maybe appropriate. If we have some information, some prior knowledge about the system, then maybe we make an initial estimate that's close to an answer that we had calculated for a similar problem before. But our examples that we're going to do in a few minutes will focus on just starting with the zero vector. There are sometimes in certain situations good choices that can be made, better choices that can be made for the starting position, but some initial estimate to get started. Then what's going to happen with an iterative method is that the new estimates that we get are based on the previous estimates. So we will get a first estimate. After the initial guess, we will get another one that will be based on the initial. First order methods only use the previous estimate each time through. So you use the initial estimate to get the x1. You use x1 to get x2, x2 to get x3, and so on going forward. There are some higher order methods. Second order methods will use two initial values to get the next one, and then the previous two to get the one after that, and keep going by twos. Similar to maybe something related to like the Fibonacci numbers that are based on a starting point of two numbers, and then you add those two together to get the next one, and then you take the two that are at the end of your sequence, add those together to get the next one, and so on and so on. So iterative methods can be simple, using a previous estimate to get a next estimate. They can be more complicated, using several previous estimates to build a following estimate. Usually, better initial estimates will lead to faster convergence. If the sequence converges at all, then starting closer to the right answer often gets you to the right answer more quickly. There are situations where iterative methods, even having a better initial estimate than some other situation, has some strange characteristics and will lead you away from the correct answer. So with iterative methods, there's not always a sense of guaranteeing that you're going to get to a correct answer. The iterative methods are definitely not exact because there will be rounding, there will be some approximation going on, and they usually don't give spot on correct answers. And in some cases, they're not even able to get very close to real answers, depending on the structure of the problem, depending on some other scenarios. The iterative methods can sometimes only get you so far, but usually they will be quick about it, at least. And so in perfect scenarios, you can at least get very, very, very close to a correct answer, and usually do so very quickly. So if the sequence of guesses does converge, then it will only be an approximate, although in some examples that we might do, the approximation it does eventually run into the correct answer. But in real life situations, don't expect that these iterative methods will give you the correct answer. And in fact, the other methods, the direct methods with floating point arithmetic, may not give exact answers, the correct answer either, because of various issues with the floating point errors that can arise. So how fast we can get to an answer, even if the method converges, and even if it converges to the correct answer, the speed of this will depend on features, aspects, typically of the coefficient matrix A in this context. So as we're going through these iterations, the question should come up of, when do we stop? At which point do we say, we're close enough, that's the answer that we're going to go with. And there are multiple ways to determine when we should terminate the procedure. So one approach is to specify the number of iterations that we're going to allow. Maybe this is a time consideration, an actual clock time consideration. Or maybe it's we're going to do this for 10 steps or 1,000 steps or 1,000,000 steps. And whatever answer we have at that point, we're going to accept as our answer. And there are pros and cons to that. Pros to that there are some iterative methods you can pre-calculate based on the matrix, the coefficient matrix, how many iterations are needed. And these things will sometimes involve what's called the condition number of the matrix. Sometimes it's things about eigenvalues of the matrix that we can calculate ahead of time and then know how many steps the algorithm or the iterative method will need to get to the right answer. This usually requires either some heuristics, which are kind of rules of thumb, or doing these extra calculations to know how many steps are going to be needed. But again, sometimes it's just a matter of we need to find an answer and we have this much time to do it, so let's use that time, and at the end of that time, let's accept whatever answer we have found. So there are reasons, there are real life situations when we would pre-specify the number of iterations we're going to allow and then just take the best answer that we found after that many iterations. Another situation is if at some particular time, if our value a times the current x, if that's almost equal to b, or another approach is a times x minus b if it's very nearly equal to the 0 vector. And so in other words, in that situation, we say let's stop if our current guess pretty much solves the system. Right? If it comes really, really close to solving the system. Now, what is really, really close? What does nearly equal mean? And there can be discussion at different situations where you change the way you're measuring the how close one vector is to another. So you use different norms. And so maybe you want the overall length to be nearly 0. Maybe you want individual positions. So there are different approaches in terms of determining how close you are to the correct answer. Another termination procedure sometimes is if subsequent estimates are really, really close together. If they're exactly the same, then what's going to happen? If you put in xt, right, the teeth estimate, and get out the same answer, then you're going to get the same answer from then on. So sometimes you would say, well, if I get the same answer twice in a row, I might as well stop. I'm not going to get any other answer. But sometimes we say, instead of getting exactly the same answer, what if the two estimates, consecutive estimates, are almost the same? They're very, very, very close to being the same value. And in that case, sometimes we go ahead and stop, but we might have been focusing in on the wrong answer at that point. So that's a situation that can happen sometimes. And another thing that can happen sometimes is the sequence of estimates can kind of compress for a little while and then change drastically before finally narrowing in and focusing on the correct solution. So we may think we're narrowing in or focusing on a correct solution and actually not be doing that. Sometimes with termination, there's a kind of a combination of different of these approaches that if these values have been nearly equal for a specified number of iterations, instead of just one followed by another being close to the same, we've done this for 100 iterations in a row and they've all been really, really close to the same, maybe we go ahead and stop at that point. So there are combinations we can create of different termination procedures, but the underlying aspects or the underlying concepts of most of the termination procedures is some version of one of these three that we're discussing now. So let's look at an iterative method called the Richardson iteration method. This is named after an early pioneer who used ideas of a pioneer of mathematics who used these ideas to do weather prediction, weather forecasting. And although he had to solve lots of systems by hand and do a lot of work because this was well before there were any good computing devices, he was able to at least show that the weather forecasting idea is valid, even though his calculations ended up, in some cases, being far off the mark. It was easy to determine what kind of physical assumption had led to those incorrect conclusions. So, first order Richardson iteration method is going to again be first order. So we're going to have one value that predicts the next value or estimates, gives us the method for estimating the next one, and we keep doing that until we get to a particular solution. Again, we're solving a square system, a times x equals b. And so the idea of the method is based on some algebraic manipulation of the system. We don't know x, but we're going to manipulate this a little bit and take a look at some things that happen. So if a times x is equal to b, then we can multiply both sides of that by a number, and we still have equality. Now we've specified here that it's non-zero, but I mean it's true if it is zero as well, then just zero, the zero vector is equal to the zero vector, but that's not very meaningful and that doesn't help us do anything. So we're going to only consider these alpha values that are non-zero. And we'll specify in a bit a little bit of an idea of what to choose for alpha. Well, in this case, it then follows that if I add x to the left-hand side, but then immediately subtract it back off, then it hasn't changed anything. The equality is still there. But this is one of those kinds of tricks that we do sometimes to work with an equation, add something on and subtract it back off so that we can factor something or reformat something to get an answer that we can work with. I had a professor once that told me that if something works once, it's a trick. If it works twice, it's a technique. And so this is a technique that we have actually seen in lots of other previous situations, probably throughout your mathematical career. Add something on and subtract it back off. Completing the square, you do something like that. Add something and subtract it right back off. And so if we do this, then we can factor that x out of the two values, the alpha times a times x minus x, factor that x out, and we have alpha times a minus the identity matrix times x is equal to alpha times b. And so we can then solve that for x and have x is equal to negative this quantity alpha times a minus I times the vector x plus alpha times b. Now that doesn't really help any in a real life sense because we have an unknown x on the left-hand side and an unknown x on the right-hand side. We can get rid of the braces and rewrite this. Well, I guess we didn't get rid of the braces, but we got rid of the negative sign out front at least, and rewrite this in this form. And what we're going to use is we're then going to use that idea as our iterative process. The x on the right-hand side is going to be the previous value, or start with our initial guess, and then we're going to create an output value and then feed that one in and get the next value and keep doing that in this process. Keep feeding values, getting out a new one, and eventually, at least in nice settings that will converge to an x that is actually the x solution to the system. So specifically, the method says that first of all, we select our alpha. And selecting the alpha, we have some technical decisions to make that are based on the coefficients in the matrix A. And so the alpha has to be selected so that certain conditions are met that basically will ensure that the sequence does in fact converge. We're going to, with the examples that we do in our calculations, try an alpha. If that alpha doesn't work, then we'll try a different alpha. And the time spent with a guess will not be that much because the process will work typically rather quickly. And so if we don't like the answer we get, we can try a different alpha, or we can try a different initial estimate. So we're going to set t to be 0 because that is the idea of time being time 0. And so our initial guess at the starting point is, let's just start with the 0 vector. And so we will repeat a process until the stop condition is satisfied. The stop condition is whichever stop condition that we chose from either amongst the 3 that we mentioned or some variation, some combination of those. So whatever stop condition we determine, we're going to repeat our process until that condition has been satisfied. And what we do is what we just mentioned is the current x value, do the calculation on the right-hand side, and that outputs the next x value. And then we increment the t by 1, so we're going on and keep doing that until the stop condition is satisfied. So we have t equals 0. T equals 0 gives us an x1. Now t is 1, and we do this again. So we're using x1 here, and that gives us x2. Now t is 2, so we put x2 here. That gives us x3, and we keep going until the stop condition is satisfied. Either we've done enough calculations or we're close enough to the right answer, and we then output that last value. We output the appropriate xt. Now, in this case, we had looked at t plus 1 before, but then we increment t, and so the value is whichever was the last one. So we are outputting the last approximation that we calculated. And so this method of the first order Richardson iteration will give us, at least if the matrix A is not overly susceptible to minor variations, then we will be able to converge to a solution and do so in a reasonable amount of time. So let's use this method, first order Richardson iteration, to solve a 2x2 system. So we're going to look at a 2x2 system that we could solve by some other method. We could solve this probably even by graphing, or solve it by substitution, or any of the other methods that we've discussed earlier. But we're going to use the Richardson iteration method so we can see how it works and then be able to compare the results of it to the actual answer, and then have some confidence when we apply first order Richardson iteration to problems that we can't readily solve by hand. So the first step is we select our alpha, and we're going to select alpha equal to 1/2. There are some features of alpha equal 1/2 that guarantee that this will converge. Often, again, as I mentioned, we're going to experiment with this line right here. Experiment with different values of alpha, experiment with different values of the starting estimate. In this case, though, alpha 1/2, and our x0 is just the 0 vector. Again, it's a column vector, but we're writing it as a transpose of a row vector in this case. All right, so then x1 we calculate by putting in the x0, putting in the alpha, A, and B, the identity matrix, all of these other pieces, I, alpha, A, x0 is a known value now, alpha was known, B was known, all of these are known, and so it's a straightforward calculation, and we get that x1 is the vector 1/2, 0. We feed that in to get x2. x2 is 1/4, 1/4. Feed in x2 to get x3, and then we just keep doing that until we satisfy whichever stopping condition that we have determined. It would be to your advantage to carry this out either by hand, or you could use a spreadsheet or write some Python code, and then compare that to the real answer to the system and see how long it takes to get there. Then, if you apply this to larger systems, for small systems, sometimes a method looks like it's a lot more work, but then for larger systems, you can start to see that the amount of work, the number of calculations that are needed, the number of iterations, are possibly much smaller than would be necessary if we were trying to apply one of the direct methods to solving the system. All right, as usual, feel free to ask questions in the comments, by email, or on Discord.